All right, let's talk about something you've definitely run into, probably without even realizing you were doing some serious chemistry. We're going to dive into the science of enough.
You know that feeling, right? You're all set to make a giant, amazing strawberry smoothie. You've got a whole carton of milk, but when you look in the fridge, you've only got like 5 strawberries left. That moment, that frustrating moment where one ingredient just kills the whole plan, that's exactly what we're talking about today. You can only make as much smoothie as your strawberries will let you. So let's just put some fancy words on this. In the kitchen, we've got ingredients, right? Strawberries and milk. And they make a product, our smoothie. Well, in a chemistry lab, it is the exact same idea. We just call the ingredients reactants, and what they make is called the product. Same game, different names.
So let's really dig into this smoothie problem first, because once you get this, you get the whole concept. We gotta figure out what's really holding us back.
So that one ingredient you run out of first, it has a special name. It's the limiting reactant. It's the one that gets totally used up, and because of that, it just stops everything cold. No more strawberries means no more smoothies. It's the ultimate bottleneck. And understanding this is the key to everything from baking a perfect cake to making life-saving medicines without a ton of waste.
Okay, so we've got the kitchen down. Now let's take this idea and walk it over to the lab, where figuring out this limiting ingredient is absolutely 100% crucial.
So how do chemists actually figure this out? It's not like they could just eyeball it. Well, the strategy is kind of brilliant. You basically create a competition. You pretend only reactant A exists and calculate the absolute maximum product you could make. Then you do the exact same thing for reactant B, completely ignoring A. It's a head-to-head race to see which one taps out first.
And this whole race boils down to a super simple 3-step game plan. First, you get everything into the same language by converting grams into moles. That's just chemistry's way of counting stuff. Second, you look at the recipe, the balanced equation, to see how much product each one could possibly make. And third, and this is the best part, you just look at your 2 answers and pick the smaller one. That's it. The lower number tells you who the winner or loser, I guess, of the race is.
Let's put some real numbers to this. Okay, competitor number 1. We start with 9.05 grams of ammonia. We run it through the steps, convert to moles, check the recipe, and the math says it has the potential to make 0.2657 moles of nitrogen gas. Got it. Let's hang on to that number.
Now for competitor number 2, copper oxide. We start with way more of this one, 45.2 grams. But when we run the same calculations, it turns out it can only make 0.1894 moles of nitrogen gas. Okay, now we have our second number.
And now for the moment of truth. Let's put those 2 results side by side. I mean, look at that. It just jumps right out at you. Even though we started with way more copper oxide, it's the one that's holding us back. It sets a much lower ceiling for how much we can make.
And that's the whole secret. The reactant that can produce the least amount of product is your limiting reactant. End of story. The whole chemical reaction will grind to a halt the second that last bit of copper oxide gets used up. It doesn't matter how much extra ammonia we have lying around. Okay, so now that we know what our limit is, we can figure out what a perfect, flawless 10 out of 10 result would look like. In chemistry, we call this the theoretical yield.
Think of the theoretical yield as the high score. It's the absolute maximum, the most product you could ever dream of making. It's a perfect world number that's based entirely on that limiting reactant we just found, is what you'd get if everything went 100% perfectly.
And finding it is easy. We just take that smaller number we found a second ago, that 0.1894 moles of nitrogen, and we just convert it back into grams so it makes sense in the real world. And boom! In a perfect world, we'd make exactly 5.31 grams of nitrogen. That's our target.
But come on, we all know the real world is never perfect, right? So let's get real for a second and talk about what happens when lab work gets, well, messy.
This is where the actual yield comes in. This isn't some number you calculate. This is what you can physically touch. It's the stuff you scrape out of the beaker at the end of the day, put on a scale, and weigh. It's the real deal. And yeah, almost 100% of the time, your actual yield is going to be lower than your theoretical yield. And there's so many reasons why. Maybe the reaction just got lazy and didn't finish. Maybe some of your ingredients decided to make something totally different. Or, maybe you just spilled a little bit. It happens to everyone.
So if we know we're never going to hit that perfect score, how do we know if we did a good job? How do we grade ourselves?
We use a little something called percent yield. Honestly, the best way to think about it is like a grade on a test.
It's a super simple comparison of what you actually got versus what you hoped to get. It tells you exactly how efficient you were.
And the formula for your grade couldn't be simpler. It's just your actual yield divided by that theoretical perfect score yield times 100. That's it.
Let's finish up our example. Our theoretical perfect score was 5.31 grams. Let's say we finished our experiment and we actually made 4.61 grams. We just plug those two numbers into our formula and we get a percent yield of 86.8%.
So, is that a good grade? You bet it is. In the real world of chemistry, getting over 80% is considered very good, and if you top 90%, that's excellent. So, 86.8%, that's a solid B+, a result you can definitely be proud of.
So why does this all matter so much? Well, this quote really hits the nail on the head. Imagine you're making a complex medicine that takes like 20 different steps. If even one of those steps has a bad percent yield, it can completely tank the whole process. We're talking huge amounts of wasted materials and money just going down the drain.
And that leaves us with one last question to think about. If in the world of multi-billion-dollar drug manufacturing, a 90% yield is considered excellent, what on earth happens to the other 10%? Where does all that wasted time, money, and chemical material actually go? It's a question with some pretty massive consequences.